All right, hello everybody. I'm just going to pick up essentially where we left off today with just a little bit of review of what we were talking about. So remember we were looking at this function here, g of x, and an absolute value function. And we discussed today how when you're taking the absolute value of something, the idea is you can just say that it's equal to that thing as long as it's 0 or greater. And so what we said is let's figure out when it is that x squared minus 4 is greater than or equal to 0. And what we found from that was that that happens on the interval negative infinity to negative 2, and then to infinity. And we created a sign, factored this out, created a sign chart, and that's what gave that to us. So here, I'm just going to write it as we get x squared minus 4 when x is less than or equal to negative 2, or when x is greater than or equal to 2. But when what you have inside the absolute value is negative, you've got to take the opposite of that to basically make it positive again, right? So we get the opposite, negative x squared plus 4, whenever x is between negative 2 and 2. And so we talked about the graph of this. So between negative 2 and 2, you just have a parabola that is facing downward. And so we got this picture here. But then outside of that interval, it just looks like this, which is an upward facing parabola that's been shifted down 4. So we can just kind of see these sides of it here. And so basically we had a situation that looked like this. And what we really had down here at negative 2 and at 2 was a corner, right? This graph's really coming to a corner. And so what we discussed today, and this is kind of where we ended, was when you have a corner, it doesn't really make sense to talk about the derivative, because really there are infinitely many tangent lines, right? Lines that only touch the graph in one spot. There are infinitely many that I could draw here that would suffice as tangent lines. And so it doesn't make sense to talk about a derivative there because it's not well defined. So what we discovered is that g is not differentiable. Can't take the derivative at negative 2, I should say, and 2. So you can't take the derivative there. All right. Now the part we didn't talk at all about today was the second part where it did say find g prime. I don't think I'm going to bother to do that this evening. Rather, what I think I'll do is encourage you to confirm the following: that g prime is equal to 2x when x is less than negative 2 or x is greater than 2. And the reason, of course, I took the equal away is because we decided we can't take the derivative at negative 2 and at 2. And then confirm, again using the limit definition of the derivative, that you get negative 2x when basically you're using this rule right here. And that happens when you're between negative 2 and 2. So confirm for yourself that this makes sense. If nothing else, it's just a good review problem for Tuesday's test, because the limit definition of a derivative, of course, is a part of that. All right, so what I want to talk about now is a little bit about how differentiability and continuity go together. And so what this theorem here is essentially saying is that if you have a differentiable function, it must be continuous. Okay, so you're not going to find a way of being differentiable if you are not continuous as a function. So, or I should say, you're not going to be differentiable at a spot if your function is not continuous at that spot. So I'm just going to show a quick proof of this, just because proofs are things that you're going to be exposed to throughout calculus and other classes that you take, and so this one's pretty straightforward, pretty understandable, I think. So I just want to kind of show you this one. So the thing here is the thing we know, that f is differentiable at a, and this is the thing we're trying to prove. So let's just over here note what this really means again. Remember, if f is continuous at a, that would mean that the limit of the function as x approaches a is just equal to the function evaluated at a. That's the definition of continuity that we had from before. So that's what we're trying to prove, but the thing that we have to work with is what's in blue here, that f is differentiable. So if f is differentiable, what that really means is that f prime of a exists, and we know what f prime of a looks like. What I'm going to do is I'm going to use the limit definition we use a little bit less, but you'll remember this from the other day. The limit as x approaches a of f of x minus f of a over x minus a. That's the limit definition of a derivative. We introduced it the other day, even though we use the one that involves h a little more regularly. But of course you might be able to see why I'm doing that, because this involves f of x and f of a, so this is probably a little more useful. So what I'm going to do here is, when I want to show that two things are equal, sometimes what's easier to do is try to show that when you subtract them you get 0. Oops, sorry, that's supposed to be an x. So the idea is, if I can show that this thing is 0, then that must mean these two things are the same. So way over here on the right side, I wouldn't eventually get to those two things being equal to 0. And so my first step in doing that is to realize that because f of a is just a number, I can actually pull that inside the limit notation. That's okay for me to do. So I can say, all right, this is the limit as x approaches a of f of x minus f of a. There's no harm in that. But then what I can also do is I can, if I want, I can multiply the top and the bottom by the same thing, x minus a. So I'm taking the limit of all of this, where I've just, cleverly multiplied by 1. But we also need to remember our limit laws, which say, okay, if you are taking the product of some things and then taking the limit of all of it, you can take the limit of two of the factors separately. So I can say the limit as x approaches a of f of x minus f of a all over x minus a. Sorry, that's an x. I can't get the eraser to work, so I apologize. X minus a times, let's get rid of this 0 here, times the limit as x approaches a of x minus a. Okay, so this right here, we know this thing exists. That's no problem. That's just f prime of a, right? And then this thing right here, well, we know that that's equal to 0, because if you let x go to a, x minus a is going to go to 0. So this whole thing equals 0. And so we've got what we want. We've got that this thing is equal to 0. So if that's true, then of course this must be true. And so f is continuous. So that's just a little proof, and certainly on this first exam, you're not doing 2.7 anyway, but I'm not going to be asking you to prove theorems like this at this point, but it's good to start getting some exposure to some of this stuff. All right, so let's look at another example where differentiability may not apply everywhere in a function. So we introduced this function the other day, the step function. And just as a reminder, the other day we talked about it in the context of a homework problem. So in the book, they kind of use slightly fancier type of notation here than I do. So just to understand this thing you see in the book here, that's the same thing I'm talking about when I use this notation in the notes. So remember, the step function is one in which it takes all values and sends them to the next lowest integer. So best just to start at 0. Okay, 0 is an integer, but then it's going to take everything between 0 and 1 and go to the next lower integer, which would be 0, right? So I've got a situation like this, but then that stops at 1 because then things get to pick back up at 1 because 1 is an integer, right? So we saw this the other day when working on that homework question. All right, and I can go back here a little bit as well, but the big point I want to make here is that this isn't a good example of a situation where there are places in the function where you cannot find a derivative, but this time it's not because of a corner, this time it's because it's not continuous. Okay, so what did we say in that last theorem? If our function is differentiable, then it's going to have to be continuous there. Okay. Oh, dang, I just lost it. I hit a button. Oh, and now it's gone. Okay. But the purpose of that, I lost my train of thought. The purpose of that was just to show an example of a function that is not continuous, and so therefore it cannot be differentiable. All right, one last situation that we want to take a look at here is this one. This here is the cube root of x, f(x) equals the cube root of x, and it actually exists everywhere. There's nowhere that the cube root of x doesn't exist, and it's continuous everywhere, but it's not differentiable everywhere. And the one place this one's not differentiable is right here at 0. And the reason it's not isn't because I can't make the tangent line. Okay. I'm sorry, I'm doing a poor job, but what I'm trying to do is I'm trying to draw a vertical line. So my tangent line here is vertical. And the reason that's a problem is because, if you remember, vertical lines have undefined slopes. And of course, a slope, right, is the rise over the run, and when you are vertical, you have no run, okay? So this is another situation where it's not differentiable simply because you end up with an undefined slope, okay? So we saw the 3 examples of when a function can fail to be differentiable, right? At the beginning, with example 4, we have corners, right? So you can't be differentiable there. Example 5, the step function discontinuities, that'll cause you not to be differentiable. And then if your tangent line is vertical, then we'd say it is not differentiable. So now switching gears here a little bit, now that we've really talked about the derivative quite a bit, we've got to start talking about all the many different types of notation that are going to come up when it comes to derivatives. So unfortunately, there's a lot of them. So we've been using just one of these. The first one up at the top there, you see f prime. So we've been using this one. This first one here isn't too surprising. You know, you were probably told over and over when you were first introduced to function notation that, you know, don't worry, function notation is just taking the place of the y. So if I can say f prime of x, then it makes sense that I can say y prime. These ones are going to be pretty brand new to us. So this is another very typical one, dy dx. You know, and maybe kind of think of that as kind of coming from delta y over delta x. I guess I have it written right down here. So change in y over change in x, but then you're going to let the change in x go to 0, right? So, so to basically be shorthand for this idea, that the 2x values you're finding your secant line between gets closer and closer together. This is just kind of a more concise version, I guess, of this formula. So we'll see dy dx a lot, but again, you can replace y with f, so we might see df dx. And then the other thing is we'll use this notation ddx applied to f. Okay, so that's another notation that you'll get used to. And the way you're kind of thinking of this is ddx is what we would call an operator. So you are taking the derivative of this thing. Okay, and so basically applying this operation to this function. And then these two here, we're going to use them very sparingly. We might use them a little bit in Calc 4 next fall, but we won't use these ones quite as much. But all of these are going to be pretty key to be able to use quite interchangeably as we go through our class. And then one other thing is when we want to take a derivative and then figure out what that derivative is equal to at a specific spot, we might say dy dx and then put this vertical line and write x equals a. So if I wanted you to compute the derivative of some equation and I say dy dx, I want you to find dy dx, but I wanted specifically to know what its value was at x equals -3, I would say this. And then I would know to take the formula for this, plug in -3 and give the answer. And then lastly on this page, we can take what we call higher order derivatives. So that just means take the derivative of a derivative. And this should make sense because we talked about here in this section that a derivative is itself just a function, right? We graphed it along with the original function. So if the derivative itself is a function, you should be able to take the derivative of that. And so that would be the main notation we kind of use there is either f double prime, right? And of course, if we have the x in there, f double prime of x, we use that. You can think of it as ddx applied to dy dx. But you'll see this one a lot as well, okay? D squared y dx squared is kind of a very common one. And so this notation is always kind of a little weird for people, but the best way to understand it is you have dy dx, you know, so it's kind of like maybe if I rewrite this side, it's ddx applied to, I'm going to write this way, ddx applied to y. So you can see the d squared comes from these two d's, and then there are two dx's, and so that's why the square comes after the dx in the bottom. Okay, but they all just mean take the derivative twice. And if you can take the derivative twice, of course, you can take it 3 times and more, and so you just kind of follow the pattern. All right, so in example 7, let's take a look here. They want us to find y prime and y double prime. So we know what that means now, right? So using our limit definition of the derivative, understand that y prime, right, is just f prime of x, which is just the limit as h goes to 0 of f of x plus h minus f of x all over h. And so remember, the game with polynomials, right, is, okay, let's go ahead and plug it in and then, you know, expand out everything until we can get the terms that don't end up involving h to go away. And then that'll allow us to cancel out that h on the bottom that's not allowing us to use substitution in our limit. Alright, so this thing expands out pretty far, or pretty big, before it collapses down again, but it will collapse down again. So, you know, in the brackets here, I've got my x squared plus 2xh plus h squared minus 2x minus 2h minus 8. And then over here I want to distribute that negative through. So this is minus x squared plus 2x plus 8. So I suppose I didn't need to keep these brackets on here. It doesn't really matter though, because I can see at this point that my x squared here and my minus x squared here are canceling. I can see my negative 2x and plus 2x are canceling, and I can see my plus 8 and my minus 8 are canceling. So that's all very good. So this is just the limit as h goes to 0 of what survived this whole thing. So 2xh plus h squared minus 2h all over h. And I'm going to carefully put this way up here. So this is going to be equal to the limit as h goes to 0 with h factored out on top, leaving us with 2x plus h minus 2 in there. And then my h's cancel. And when I send h to 0, of course, that term goes away, and I'm left with just 2x minus 2. So we have y prime is 2x minus 2. So if we want y double prime, we understand that y double prime, right, is just taking the formula for y prime we just took and taking its derivative. All right, so all we have to do is, okay, this is our new function now, and so we take the limit as h goes to 0, and I'm just going to plug x plus h in where I see an x. All right, so this is 2 times x plus h minus 2 minus 2x minus 2, all divided by h. And again, we're just trying to get everything that doesn't involve an h to cancel out. And that happens pretty easily. 2x plus 2h minus 2 minus 2x plus 2. And we distribute that negative through, and we do get all that cancellation we were looking for. Right, so 2x minus 2x minus 2 plus 2. So this is all just the limit as h goes to 0 of 2h over h. Right, canceling my h's, that means that my second derivative is just equal to 2. So if I want to think about the graphs of these things, I can do that. So first of all, let's think, y equals x squared minus 2x minus 8, right? So I want to graph this. I know it's a parabola, right? And because it factors, I do know that its x-intercepts just come from solving this and it factoring out into x minus 4, I guess it would be, and x plus 2. So we can see that x equals 4 and x equals negative 2. Those are our zeros. So here's one, and here's the other. And of course the vertex, because of the symmetry of a parabola, the vertex is right in the middle of the two. And I can also see that my y-intercept is negative 8, so that's going to be, let's see here, 1, 2, 3, 4, 5, 6, 7, 8. Right, the vertex is going to be at 1, and so I think it's worth me plugging in x equals 1 to see where that's at. And so 1 minus 2 is negative 1, so that's negative 9. And I also could have known that by the fact that the coefficient in front of the x squared term is 1, so there's no transformation happening here, so I know I would just be going up 1 over 1 from that vertex. And over 2 up 4. And so we get a pretty good picture here. We'll see how well I can graph it on this on the computer here. Hopefully okay. Oop, that wasn't good. And let's try for the other side here. Okay, that'll have to do. So there's my really wobbly parabola. All right, but let's talk about the other two. We know that from the previous page, we know y prime is equal to 2x minus 2, right? And so we know how to graph that. So the 2x minus 2, minus 2 is the y-intercept, negative 2 is y-intercept. And so, up 2 over 1, up 2 over 1, up 2 over 1. Okay. And let's notice this spot right here. So of course it's a line, right? So let me just go ahead and make a poor excuse for a line there. But what I want us to look at here is, right, remember what it means for the derivative to be 0? That's where the tangent slope of the original is 0, and so of course that's exactly at the vertex on a parabola, right? So that agrees. If you sketch tangent slopes along here, they have negative slopes, right? That's why we have negative y values for the derivative. And then up here, right, positive, because to the right of the vertex here, if you start sketching tangent slopes, they are, oops, that wasn't even close to a tangent slope, sorry. They are all positive slopes. We're above the x-axis. All right, and then lastly, y double prime. That was just 2, right? So that is just a constant function at 2. Maybe I'll give that a different color. Let's see here. How about, okay, so do it in that color there. So it looks like that. Now, understand that this is just the derivative of this, okay? So this thing should represent the tangent slope at various points on this graph. But look at this graph. This graph is a line. So the tangent slopes everywhere are the same, right? They would always have a slope of 2, no matter where you drew them, because they'd just be lying right on top of the curve itself. So it makes sense that the second derivative is a constant function because the tangent slopes here are never changing. Okay, so just to kind of give you an idea of this layering, that you can just keep taking more and more derivatives, and it's giving you information about the derivative that's just one order lower than it. So lastly, what I want to just kind of wrap a bow on here is in part C, what is the meaning of y double prime? Well, to put it very simply, y double prime gives the rate of change of y prime, right? That's the thing that I want us to really grab onto here. All right. So the last piece of this lesson here is I do want to talk about applications of derivatives. Okay, and we've already run into this once or twice, where we talked about how the first derivative of some sort of function that describes motion is going to be velocity, and I'm kind of reminding us of that here. So if S represents the position of some object, then S prime is just simply the velocity of that object at a particular time. So we might say v of t for velocity, we might say s prime of t, we might say ds dt, right? All those are valid notations. But now let's talk second derivative, okay? So what would second derivative be? We just said on the previous page that the second derivative is the rate of change in the first derivative. So to put this in a familiar context, it would be how fast is my velocity changing? So let's put ourselves in a vehicle for a second. If we are going to increase velocity, what are we doing? We're hitting the accelerator. We're accelerating, right? If we hit the brakes, we are decelerating. So the second derivative of position is the first derivative of velocity, or in other words, the rate of change in velocity, which we know as acceleration. So in this context, the second derivative is acceleration. Okay, so let's keep that in mind as we do this last example here. All right. So, all right, so in this last, oops, I got the wrong page up here, sorry. In this last example, we're going to take a look at an application. So the ball is dropped from the top of a building, and its height in feet after t seconds is given by h of t. We have the graph there for us, and in part A wants us to approximate h prime of 1. And so we've done this kind of thing before, right, where we're finding the point that we're really interested in here. So h of 1. And then we just do our best to sketch in our tangent line. And I'm not doing a great job here, but we'll see here. All right, so we do our best at that, and I didn't do a great job. But and then we look at, okay, well, what is our change in x? What's our change in y for this line we've made? And so, okay, my change in x here is about 2. And then my change in y, well, it's a negative, right? We're dropping, and so I don't know. I'm going to call that negative 50. You know, that's a ballpark. But so what I could say over here is that h prime of 1 is approximately, right, negative 50 over 2. Right? Remember that negative is important, right? Because it tells me not only how fast this ball is, but in what direction it's going. So it's falling because of that negative symbol. So so what does it all represent, right? Well, the first derivative is velocity, right? So we can say, you know, after 1 second, the ball is falling at a rate of 25 feet per second. Right? So then part B says, what is the approximate velocity of the object when it hits the ground? Okay, so of course that's right here. So I want to do the same thing. I want to try to ballpark a tangent line, which is going to be a little tough. I'm going to call that good right there. That's about as good as I'm going to get. So so let's look at this. Okay, I've got a change in y here. Oops, having trouble making a straight line. A change in y, oh gosh, let's call that, I don't know. That looks to me to be about a height of maybe 80, and then it falls down to 0. So I'm gonna call that change in y of negative 80. And then this seems to maybe cross it around 5.5. So I'm going to call my delta x in this case 1/2. So if I do that, then what I can say is that the velocity at that point, and you know, and we don't have an equation for this, so I don't know this exactly, but I'm going to say the velocity is basically h prime of 5.5, 5.5, just because that looks like the time it's crossing or going to the ground. So I'm going to say that that's about you know, negative 80 over 1/2, which is just going to give me negative 160, negative 160 feet per second. All right. So what we can see here is we had negative 25 feet per second after it was falling for 1 second, and after 5.5 seconds, when it hits the ground, we're all the way at negative 160 feet per second. So it says, based on your answers from part A and B, as well as the graph, would the graph of h double prime be above the x-axis, below the x-axis, or both? Okay. I encourage you to pause right now and actually think about this one before I give the answer. All right. So I'm assuming you've paused and thought about it deeply. But hopefully you came up with that h double prime, right, is below the x-axis. Because let's think about what's happening here. If h double prime, right, is the change in my first derivative, then what's happening to my first derivative? My first derivative is getting more negative, or in other words, it is decreasing. Okay, so h double prime is below the x-axis, right, because h prime is decreasing, right, which would mean, in other words, tangent slopes of h prime are negative. And since h double prime is the tangent slopes of h prime, you know that it would have to be below the x-axis. Okay, so I'll see you all Monday. You know, I know that my handwriting's sloppy on this thing, and it's actually late at night for me, so if anything wasn't really clear, make sure you ask me about that on Monday so we can make sure we get things cleared up. But other than that, have a nice weekend.